This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 8 of Week 3. Natural convection, also called free convection. The fluid moves on its own, driven by buoyancy, with no fan and no pump. We'll meet the expansion coefficient beta, the Grashof number, and the Rayleigh number. Then plug Rayleigh into the Handbook's power law correlations for a vertical plate and a horizontal cylinder. In forced convection, something external pushes the fluid. A fan, a pump, the wind. In natural convection, there's no external driver. Heating changes the fluid's density. A hot surface warms the fluid touching it. Warmer, less dense fluid rises, and cooler fluid sinks to replace it. That self-sustaining circulation carries heat away. Notice what's missing. Nobody hands you a velocity. You compute the flow strength from the temperature difference and fluid properties. The telltale exam words are still air, quiescent fluid, or stationary fluid. Buoyancy strength depends on how much the fluid expands when heated. That sensitivity is the volumetric thermal expansion coefficient, beta, in units of 1/Kelvin, the fractional density drop per degree. For an ideal gas, it collapses to beta equals 1/T, with T absolute in Kelvin. The Handbook writes it as 2 over the quantity T surface plus T infinity, just 1 over the film temperature. One warning that costs points. Beta always uses absolute temperature, Kelvin, never Celsius. And for a liquid, beta is a tabulated property, not 1/T. Same 4-column shape since week 1. Quantity, symbol, units, source. Up top, fluid properties, beta, kinematic viscosity, conductivity, Prandtl number, all from a property table. The middle group, the 2 boundary temperatures, and the characteristic length. The bottom, what you compute, Grashof, Rayleigh, and the film coefficient H. The rule that ties it together. Every fluid property is evaluated at the film temperature, the average of surface and fluid. Picture a vertical wall hotter than the still air around it. A thin layer of air against the wall heats, becomes buoyant, and rises, a boundary layer growing from the bottom upward. That rising plume is the entire transport mechanism, driven only by the surface-to-fluid temperature difference. For a vertical plate, the characteristic length is L, the plate height in the flow direction. Notice on the diagram, the boundary layer starts thin and laminar at the bottom, thickens as it climbs, and high up can go turbulent. That transition is what the 2 rows of the correlation table capture. Natural convection gauges flow strength with the Grashof number, which compares the buoyancy force driving the flow to the viscous force resisting it. Grashof equals G times beta times the temperature difference times L cubed over kinematic viscosity squared. The temperature difference is surface minus fluid. Kelvin equals Celsius for a difference. Notice the L cubed. Natural convection is extremely sensitive to size. Double the length, and Grashof jumps by a factor of 8. But the correlations take the Rayleigh number, Grashof times Prandtl, not Grashof directly. That's the form the Handbook prints. It lists Rayleigh with Prandtl already folded in, never a standalone Grashof. Rayleigh decides which row of the table you use. Both Handbook correlations share one shape. Compute Rayleigh, read C and N off the matching range, and H drops straight out. The vertical plate uses height L. H equals C times K over L times Rayleigh L to the N, with a 2-row table splitting laminar from turbulent. The horizontal cylinder, a bare steam pipe, a heated rod, uses diameter D with a 4-row table. Build Rayleigh D with D cubed in place of L cubed. Everything else is identical. One note for textbook users, the Churchill-Chew correlation, a smoother fit valid across all Rayleigh numbers, is not in Handbook 2.0. On the exam, use these simpler power law tables. Sometimes a problem has both buoyancy and a forced flow, a warm pipe in a light breeze. Which controls? The rule of thumb compares the buoyancy parameter, Grashof, to the forced flow parameter, Reynolds squared. Much greater than 1, buoyancy dominates, natural convection. Much less than 1, inertia dominates, forced convection. Around 1, mixed convection, and both matter. Quick screen. If Grashof over Reynolds squared exceeds 1, lead with natural convection. One caveat. This ratio is an engineering rule of thumb, not a Handbook formula, with no citation. Use it to choose your approach, then solve with the cited correlation. Worked problem. A vertical wall section, 2.5 meters tall, 4 meters wide. Its outer surface sits at 50 Celsius in still air at 20. Air properties are taken at the film temperature, 35 Celsius or 308 Kelvin. Because air is ideal gas, beta is 1 over the film temperature. Find the natural convection heat loss rate. Notice, no velocity given, so this is unambiguously natural convection. Build the Rayleigh number. G beta delta T L cubed over nu squared times Prandtl. The temperature difference is 30 Kelvin. Working through, the Rayleigh number lands at about 4 times 10 to the 10th. That falls in a turbulent row, so C is 0.10 and N is 1/3. Now, get H, then Q dot. H equals C times K over L times Rayleigh to the N, giving about 3.6. The wall area is height times width, 10 square meters. Then Newton's law of cooling, Q dot equals H times area times the temperature difference, about 1090 watts or 1.09 kilowatts. A check, an H near 3.6 for still air sits in the natural convection to air band, roughly 2 to 25. See H in the hundreds, and you've slipped. Final answer, about 1090 watts, roughly 1.1 kilowatts. Quick checks, units resolved to watts. Regime, Rayleigh passed 10 to the 9th, so the turbulent row was correct. The coefficient near 3.6 sits in a natural convection to air range, and 1 kilowatt off 10 square meters at 30 Kelvin is modest, as expected for free convection. No velocity was given, so Grashof over Reynolds squared isn't even defined, pure natural convection. And note, that's the convective loss only. A real wall also radiates, but the problem asked only for the natural convection part. 5 traps that quietly cost points. 1. Using Celsius for beta. The ideal gas beta needs absolute temperature, Kelvin. The temperature difference is fine either way, but beta is not. Number 1 slip. 2. Wrong characteristic length. Vertical plate uses height L, horizontal cylinder diameter D, and since Rayleigh scales with length cubed, a wrong length wrecks the answer fast. 3. Wrong C and N row. Compute Rayleigh first, then match the range. Don't default to laminar. 4. Forgetting the Prandtl factor. The correlation's key on Rayleigh, Grashof times Prandtl, not Grashof alone. 5. Citing Churchill Chew, which is textbook, not in Handbook 2.0. The Grashof over Reynolds squared test is a rule of thumb with no citation. A 6th, always evaluate properties at the film temperature. Bookmark the pages. Vertical plate and horizontal cylinder sit on facing pages. Fold the corner. Recall card. Ideal gas beta is 1 over the film temperature. Equivalently 2 over the sum of surface and fluid temperatures. Always absolute. Liquids come from a table. Grashof is G beta delta T L cubed over nu squared. And Rayleigh is Grashof times Prandtl. Vertical plate is H equals C times K over L times Rayleigh to the N, 2 rows. Horizontal cylinder is the same with diameter D, 4 rows. Always evaluate properties at the film temperature. And the natural versus forced screen. Grashof over Reynolds squared above 1 means natural dominates, a rule of thumb with no citation. Up next, Topic 9, Radiation Heat Transfer. Topic 8, Close the convection arc. Natural convection joins the forced convection of Topics 6 and 7. Radiation is the third and final mode. We leave fluids and boundary layers behind and meet the Stefan-Boltzmann law, emissivity, and why radiation, with its fourth power dependence and insistence on absolute temperature, dominates at high temperatures, and couldn't be ignored even on the wall we just solved.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.